السلام عليكم. هذا الفيديو هو مراجعة سريعة للسيركت اللي كتبناها اليوم as a code, which is the complementary CMOS inverter. In the example that I had my VDD of the circuit equal to 5 volt. W over L for the NMOS was 2.5 micro على 0.5 micro. W over L for the PMOS was 5 micro over 0.5 micro. We were able to plot V output versus V input, which is the voltage transfer characteristic, to obtain V output high, V output low, V input low, and V input high of the plot. Then you will be able on your own of calculating noise margin low and noise margin high. Next, we plotted V static versus V input. We didn't plot IDD versus V input. It's okay. We were able to get the value of IDD low, IDD high, and IDD peak by plotting the power plot. Next, we change the settings in the circuit such that we were able to plot V output and V input versus time to get propagation delay low to high, propagation delay high to low, and finally the total propagation delay. The first thing we did, we took our circuit and we numbered the node in our circuit. As I said earlier, the nodes that we numbered are the node that has two components connected together or more than two components connected together. So the first step I did is as follows. I took the circuit, as you can see over here, and stated that the ground node is always numbered 0, so I don't need to actually identify a number for it. And then I took my circuit and numbered it as follows. The node between VDD and source and bulk of the PMOS was numbered 1. The input node was 2. The output node was 3. Then I asked you in our circuit how many components we have. And we said that we had 4 components, 2 of which were similar, which are the voltages, and then we have the 2 transistors, which are NMOS and PMOS. For the 2 voltages that we had, we said that VDD is a DC voltage source all the time, while the input or V input could be a DC or a pulse voltage source depending on what we have to plot. In the first plot, we wanted to plot the voltage transfer characteristic, so we set V input to be a DC voltage source. Find the voltage source. We said that in the general format of PSPICDE AD, we had the voltage source named or code written as follows. We first name the voltage source, add the positive and negative node of the voltage source, identify its type, which is in our case DC, and then we add the value. Here I had already written the code for VDD, since in my example the value of VDD is 5, and I numbered the node of VDD to be 1. My line code was VDD, positive terminal of VDD was node number 1, negative terminal was the ground, the type of voltage source VDD is DC, and finally the value of VDD was 5. For V input, we said that the input is between node 2 and node 0. For the voltage transfer characteristic plot, we wanted V input to be DC, and we can add whatever value for V input since we are going to sweep it. So here's my V input. The input node was 2, 0. Positive node was 2, negative node was 0. Then the type of my V input voltage source was DC, and in my case I chose the value of V input to be 5. You can choose it to be 0, you will get the same results. Transistors, we said that the general form to writing the transistor code will be M with the name of the transistor. We said that we will name them as number M1, M2, M3, and 4, and so on. Then we will write the number of the drain node, then gate node, then the number of the source node, and finally the number of the bulk or substrate node. Then we will write the model name of each transistor, what is the value of the L and what is the value of W of the transistor. In our circuit, or in my example, for the NMOS, W is equal to 2.5 micro, while L, the length of the channel, is equal to 0.5 micro. The NMOS model was CMOS N. To define my M2, which is NMOS, I said that the name of the NMOS is M2. The drain of NMOS was at the top, which is node number 3. Then the gate, node number 2. Finally, the source and bulk are connected to ground, so node number 0. NMOS transistor, adding the numbers of the node for each terminal, I added next what? I added the transistor model. For NMOS, as we said, it was CMOS N. Then the value of L, 0.5, value of W, 2.5. طبعا don't forget the units. Next, I want to define the PMOS transistor. For the PMOS transistor, the source is usually at the top and the drain is at the bottom of the transistor. So here, the name of each terminal. So for PMOS, the drain will be at the bottom, the source is at the top. To identify the source from the drain, the source will always be connected to the bulk or substrate of the transistor. So for PMOS, the name of the transistor will be M1, the drain node 3, gate 2, then source and bulk 1, 1. Model name CMOS SP, and finally L equal to 0.5 micro, W equal to 5 micro. And here I have defined it as I said it just now. Now, if you have the circuit and you want to identify if your circuit has NMOS or PMOS transistor, look at the bulk. If the bulk arrow is pointed into the gate, so it will be an NMOS. If the bulk arrow is pointing out of the gate, it will be a PMOS. MOSFET model. You already have the MOSFET model in the text file available in the assignment link. This is almost the same model. We will notice that for the model we have first a dot to identify. It's an instruction to edit the parameters of the transistor. Then what is the instruction? Model. Then the name of the model, which is CMOS SN, and then the type of the transistor this model is for. So here, this is dot model CMOS N, and the transistor used in this case will be, or this model is for the NMOS transistor. The circuit code that you have already written. We can say this dot model, then CMOS SP, the name of the model, then the type of the transistor, which is PMOS. Please note that inside the transistor model, every new line should start with a plus. If the line doesn't start with a plus, you could have an error when running the circuit. Which is the voltage transfer characteristic. We said that we need B input to be the x-axis. So to do that, we needed to add the line code for the DC sweep analysis. The general form is dot DC, then the source that you want to sweep, the start value, end value, and finally the increment. For our circuit, we said that we wanted to sweep V input. We will sweep V input from 0 to VDD with an increment equal to 0.01. So the code will be .dc, the input that we want to sweep, from 0 to 5 with an increment equal to 0.01. In your case, you just have to change the end value over here to be the value of VDD that you have in your circuit. Next, we added the dot prop and finally the dot end to end our code. Result that you should have here, I had first the title line with the name of the circuit and my name, the voltages, code lines, then the transistors, code lines. I added a simplified model, and finally the .dc for the DC sweep, and ended my code with .prop.end. So what do we have to do now? What we have to do now is, first you will have to go to File, Save As. In File, Save As, make sure to save your file as .cir file. So in my case, I said that the name of my file is CMOS_example. I'll name it number 3, and then I added .cir. If you don't do this step, what will happen is the file will not be saved properly to be used later to run the circuit. So here I said save. I'll close my file. And then I'll open it again as a CIR file. So here, open. Make sure that you change the file type to .cir. My file is CMOS_example3.cir. On the play or run button over here. After running the circuit, you will have this empty slot over here. To add the y-axis that you want, you can go to trace, add trace, and add whatever variable you want. Now we have our circuit. We were able to plot the voltage transfer characteristic and the power versus the input. We next want to plot the output and the input versus time to obtain the delay in our circuit by calculating Tp low to high of the output, Tp high to low of the output, and finally obtaining the propagation delay. In our circuit, the period of the square signal or the pulse signal for the input will be equal to 1 microsecond. As we said, if we want to plot the output and the input versus time, what will change in our circuit will be the input will change to a square wave and the analysis description will be changed to transient analysis, since we want our x-axis to be a time axis. For the pulse wave, what will change is the type of the voltage source and the setting of the voltage source. So we still have the voltage name, positive node, negative node. But what changed here is what? The type of the voltage source. In the first part, V input was DC, now V input will be a pulse. The settings of the pulse include V1, V2, T delay, T rise, T fall, pulse width, and period. Here, V1 will be the initial value, which is 0. V2, the final value or the pulsed value, which is VDD. T delay will be 0. We'll set T rise and T fall as in default as 1. 1 femto, 1 femto. For the pulse width, it will be half the period. It was given that the period is equal to 1 micro, so here the pulse width will be 0.5 micro, while the period will be 1 micro. Example, Vx, in our case it's V input, is a square wave with V1 equal to 0, V2 equal to VDD equal 5, and the period equal to 1 micro. When I wrote the code for Vx, I said the following. Vx, for example, is between node 2 and node 3, but in our case it will be between node 2 and node 0. The type of Vx voltage source will be a pulse. This pulse will change from 0 to 5, so the initial value is 0, the final value is 5, with a delay equal to 0, rise time 1 femto, fall time 1 femto, which is almost equal to 0, pulse width half the period, which is 1 micro, and finally the period, which is equal to 1 micro. So pulse width half micro and period equal to 1 micro. In the pulse definition, what will change usually is the value of VDD, pulse width, and period if the given period were and VDD were different. Transient analysis, we'll write it as dot tran, t-step, and t-stop. Dot tran is the name of instruction. T-step is the number of the value of the step between each point, and t-stop is the final value in the x-axis. In our case, t is equal to 1 micro. So t-stop will be 3 times the period, so 3 micro. T-step will be 0.03 microsecond, which is, to make it easier for you, which is always equal to t stop over 100.